Let's see now the concept of a stress. So stress at a point. Stress at a point. So let's consider a body, and these are the boundary condition. Okay. Now on this body, there will be two different type of force that can be applied. One is the body force, and this body force will be experienced by each and every particle of this body. This is the body B. Okay. And another is the surface force or traction force. So this is because of the contact of two bodies or the force applied on the surface. So this is the two, apart from electromagnetic or law, I am not discussing all this. So there will be the body force and another is the surface force. So the surface force, let's say this is what the traction force is. And the body force is the gravitational force, centripetal force, and all these forces comes under the body force. So now this, if you see the definition, the body force is defined as either per unit volume or per unit mass. So if this is so, so body force can be considered as the B rho dV and volume, and the traction force we are having, the traction force is defined as the force applied on some small area, and we are integrating in order to determine, we are integrating this traction force with over ds and over the surface. This is what the body force and traction force. So actually on a body, either there is a body force, and most of the cases in gravitational force, the body is itself in equilibrium. Whatever the deformation is going to happen, it will happen, and then actually main deformation is happening whatever the traction force we are applying on the body. That is in our interest in the mechanics of deformable body. So when we are applying the traction force, what is happening, this force is getting transmitted within the body, and the deformation is occurring at each and every point of this body depending on its intensity and depending on the material constitutive relationship, how for what force how much deformation will occur. Now how this force get transmitted internally, so that we have to understand, and for that what we used to do, we are making some hypothetical section and we are considering some internal portion, and we are saying that this is this part, the part A of this body, and we are saying that there will be some internal force on this internal surface, and if this is the plane N, so this should be like this. And whether I don't know that whether you know or don't know this, that this hypothesis that internal force is transmitting, that was given by the Cauchy, and that's why it is also known as Cauchy axiom. Okay, and he also, as we are considering in the Newton's law, third law, that the force will be another surface action reaction. So in other surface you will have the traction force opposite to this, and if you are considering a very small area at here, then this traction force is defined as limit delta A tends to 0 delta F upon delta A. So this is the definition of traction vector, and this is known as traction vector. Okay, so we have seen that what traction vector is, and this whole hypothesis postulate is given by the Cauchy's, and also it is known as the Cauchy's axiom. Now let's move further. So we have a body, part of the body. We have considered a small area, and the normal to this is n. Now we are having this traction vector t. Okay. Now the question is, if I will change the normal to the plane, or I will consider the different plane. So let's say the plane is like this, then at the same point, I can have infinite number of planes, and this traction vector will depend on what plane actually we are analyzing. So if we are having the infinite number of plane, we can draw from a point infinite number of plane. So actually this t is not a constant term, rather t will vary according to its normal direction. So now the question is, how do we handle this? How do we deal all these things? So then the concept of stress evolved. Now let's consider, if I am considering a three-dimensional space, x1, x2, and x3 space, x3 space, then I can make a three independent planes here and complementary plane as well. So let's say this is x1, x2, and x3, and this is the very small area what we have analyzing at this point P. So this is representing actually point P only. Just in order to show, we have a zoomed version of the point P here. Now, as we are having this plane, x2 plane, x1 plane, and x3 plane, so it means that the normal to this x2 plane is along E2, and the traction vector I can consider, there would be a traction vector, and that is, let's say for example, T1. Similarly here also you may have a traction vector like T2. This is not necessarily parallel, this is just I have drawn, this is T3, and this is T2, and on plane 1 it is, let's say, T1. So as we have shown, on in a given plane, we have shown that T is a traction vector. Similarly, we can say that on x2 plane it is T2, on x3 plane it is T superscript T3, and so on. Now, so we can have the many infinite number of traction vector at a given point, at the same point. Now our objective is to find whether such physical quantity exists at a point which does not depend on the plane. It is independent of that. Okay, and let's consider this. If I'm considering this traction vector, I can decompose this traction vector into three. One component will be along x1, other component will be along x3. This is normal component, and then we will have the shear component. Shear component here, since it is three-dimensional, then we will have two components of the shear component, and this is similarly here also you will have along x2, then along x3, along x1, and for this also. And these, so each traction vector, if you see this plane, for let's consider x1 plane, this traction vector can be decomposed into three, and this is defined as by the term sigma 11, the component of the traction vector, sigma 12, and here we are having sigma 13. Similarly, we will have hello. Yeah, similarly, we can have T2, T3, and so on. So can I write this T1 vector as sigma 11 E1 plus sigma 12 E2 plus sigma 13 E3. Similarly, we will decompose the traction vector acting on plane 2, and this we can write as T2 sigma 21 E1 sigma 22 E2 plus sigma 23 E3, and so on. We can write T3 as well. We have decomposed this traction vector T3 and in the 3, and this along x1, along x2, along x3 axis, and the equation can be written as E1 cap plus this plus this. So actually our objective is what? Our objective is to find a physical quantity that does not depend on the plane. Rather, it depends only on the point. We try to define a physical quantity at a point which is independent of the plane. As we have seen that the traction vector will depend on the plane. So for that purpose, we are now extending the concept of the traction vector. We are decomposing this traction vector into three. On each plane, we are decomposing into the first the normal component, shear component. Further, shear component can be decomposed into two in x, y, z coordinate system, and we got these equations, and we got these terms as well: sigma 1 1, sigma 1 2, sigma 1 3, sigma 2 1, and so on to till sigma 3. 9 different components we obtain. Now let's consider a tetrahedron formed by the coordinate system. Oh no, this will not help you. So for example, this is x1, x2, and x3. Now we are considering a plane having this, and this is n, and this is on this plane. Let's say you are having the t traction vector on this plane is t. So again, we are analyzing point P only. So point P, okay, just the zoomed version of point P in the considering. Now here we are having this. This is the plane normal of normal to this plane is n1, and we have the traction vector is t1. Now we are having here x3 plane, x2 plane, and x1 plane, and also we will have the traction vector. So this plane x1 plane formed by the x1 x3 axis, we are having x2 plane. So let's say the traction vector on this plane is t2. 2 is at subscript. Now plane formed by x1 and x2 axis, the traction vector, let's consider this as, this is the x3 plane, perpendicular direction is e3, so x3 plane. This is t3, and let's say the third one, the plane formed by x2 and x3 axis, that the traction vector, let's say this on this plane is x1 plane, and let's say this traction vector is t1, and this n will have component n1. I can write this n as n1 e1 cap plus n2 e2 cap plus n3 e3 cap. Okay, now by writing the equilibrium equation, you can prove this. The T can be written as T1 N1 plus T2 N2 plus traction vector on plane 3 N3. So you should try it by writing equilibrium equation. You will get this expression. I'm not going to derive this, but in any textbook or even when you will try, you will find this relation. Now we have also established that T1
procedure is to shrink the this volume, I guess.
Yeah.
Then we can get this equation, I guess.
What is your question? Can you say loudly?
To prove this, we have to actually shrink the volume of this tetrahedron.
Yeah. You consider, and also that there will be relation between area. So delta S1, delta S2, delta S3. If this is delta S, then there is a relation, because traction vector multiply with area.
Yes. Okay, I get it.
And then component you will get this relation.
Okay.
So, this T1, as we have just in previous slide, we have written as sigma 1 1 E1 cap plus sigma 1 2 E2 cap plus sigma 1 3 E3 cap. Okay, and similarly we have written for the traction vector on other plane also. If you will substitute these, whatever we have expressed here, what you will get? You will get the T vector as sigma 1 1 plus sigma 1 1 n1 plus sigma 2 1 n2 plus sigma 3 1 n3 E1 cap plus sigma 1 2 n1 plus sigma 2 2 n2 plus sigma 2 3 sigma 3 2 sigma 3 2 n3 E2 cap plus, just by substituting whatever we have obtained here, the traction vector at different planes in terms of these, the component of the traction vector here, sigma 1 3 n1 plus sigma 2 3 n2 plus sigma 3 3 n3 E3 cap. Okay, now this traction vector T can be written as T1, here 1 is subscript, okay, E1 cap plus T2 E2 cap plus T3 E3 cap, where T1, T2 and T3 are the component of traction vector at plane N along x1, x2 and x3 direction. Okay, if this is so, can I write, if this is so, so equating the base vector of T, the vector T, the traction vector T, can I write T1 is equal to sigma 1 1 n1 plus sigma 2 1 n2 plus sigma 3 1 n3. Similarly, T2 is equal to sigma 1 2 n1 plus sigma 2 2 n2 plus sigma 3 2 n3, and T3 is sigma 1 3 n1 plus sigma 2 3 n2 plus sigma 3 3 n3. Now, this is what we have obtained, the component of traction vector at plane N, what is the T1, T2 and T3 in terms of sigma, the whatever the different component of three independent planes we have decomposed, and with the directional cosines of the normal vector N. Now, can we write this in matrix form as T1, T2, T3, a vector, column vector, is equal to sigma 1 1, sigma 2 1, sigma 3 1, sigma 1 2, here sigma 1 3, sigma 2 2, sigma 2 3, sigma 3 2 and sigma 3 3. So the same equation now I am writing in a matrix form, and here I am writing n1, n2, n3. Okay, and this is nothing but the T vector is equal to sigma transpose n. This is our well-known and famous equation in the continuum mechanics or mechanics of solid, where the traction vector can be written as sigma transport, because this is sigma transport. If we are considering sigma is equal to sigma Ij, so actually this is, if you are considering sigma as this, sigma 1 1, sigma 1 2, sigma 1 3, we are putting in this order 2 2, sigma 2 3, sigma 3 1, sigma 3 2, sigma 3 3. Then if you are putting all the component in this order, then this is sigma transpose of this, because the row and column get interchanged, and that's why this is sigma transpose. Now actually here we obtained the sigma relation between the traction vector, normal vector, and sigma. But the question is, what is the unique thing in this? We all know that what is sigma, this is the stress component and all. So what new things we have find? For that I am giving the weightage to this. If you carefully see this, what this equation represent, here this consider sigma as an operator. Okay, sigma t, let's consider as an operator. You are giving here input as normal vector, and you are getting a output as a traction vector. So this sigma transpose actually linearly map from normal vector to a traction vector. Fine. Then what is physical relevance? So the physical meaning of this, that give at a point, this sigma transport is a unique quantity. The point is defined by the sigma transpose, or let's say sigma stress, and you will give normal vector, means you may have the different plane, infinite number of plane. Just give me a normal vector, I will give you a traction vector at that plane if you are having the sigma defined at that point. So the sigma is the property of point. Sigma is not the property of plane. Sigma is a unique value for a point. But traction vector is not a unique. Traction vector depend on the normal vector. So giving the normal vector as an input, we will get the traction vector as an output. And that is the very beautiful concept in mechanics of solid. And this is what the stress concept is, a very, very interesting and important. So this is what stress is. Again, stress is linearly mapping n vector to t vector. This is just a linear mapping. Okay, so this is what the stress is, and this stress can be further, this equation can be written as sigma tau I ti, initial notation I'm trying to write, ti is equal to sigma, here we will have nj, so here is ji. So this is initial notation. This is symbolic notation of same thing. And this is either written as t vector is equal to sigma transpose n vector. This is matrix notation. So same equation can be represented as matrix notation, symbolic notation, or tensor notation also it is known, or initial notation. But you must know that whatever notation it is, what actually it represents. So this is the concept of stress, and that is why in all the textbook, in all the paper, you will find stress at a point, because the stress is a unique physical quantity which represents that specific point. Obviously, its magnitude depend on the coordinate system, its magnitude depend on the load applied and all these things. But for a given condition, the sigma is a unique. It does not depend on any plane. It depends only on the point. If you will give the plane, it will give you the t. So it's just an operator giving n, you will get t as an output. So since also we know that since the sigma is a symmetric, you can prove by using the angular momentum concept, and you can prove that sigma and sigma transpose are equal. So the stress is a symmetric tensor. Symmetric tensor. Since the two directional sense are required to define this, so that's why it is a second order tensor. and it is also linearly mapping one vector to another vector. That is also a reason this is a second order tensor. It also satisfied the condition of transformation rule. So sigma dash can be written as A matrix, the transformation matrix, times sigma times A transpose. So this is also applicable to this. Any second order tensor, this must satisfy this criteria. So this is here applicable also. Okay. Any question if you have in your mind, then please ask.
Sir,
Yeah.
can you go back to the previous pages where you were defining this N1, N2, and N3 planes?
This one?
Yes, sir. So
Yeah.
initially we considered the point as a cube. So we zoomed and we considered it as a cube in the previous one.
Yes. Previous one. Yeah, we have considered
and then we started defining it in this plane, in the new plane. So why did we transform it? Can you explain it?
Okay. See, the planes are same. We have not changed the plane. Two things we have kept constant. Here we are having the first point. Okay, that is important for us. So
Yes.
this point, what we have considered, this point is our interest. Okay. So
Yes, sir.
actually our focus is point P. Now here we have make a section, hypothetical section, and we have drawn the internal force on this. This plane is defined by its normal vector, that is n. Okay. Now
Yes.
here the question is, we can at this point we can have infinite number of planes, isn't it?
Yes.
But how do we handle infinite number of plane in our analysis? So the best way is, now we will we have considered a Cartesian coordinate system. So this Cartesian coordinate system is OX1, X2, and X3. Fine. In this Cartesian coordinate system, we will have three independent planes, isn't it? Plane,
Yes.
X1 plane, X2 plane, and X3 plane.
Yes.
And in order to geometrically visualize this, we will make a cuboid. Okay. And we have shown, because we have shown here X1 plane, X2 plane, X3 plane, and complementary planes of these X1, X2, and X3 opposite to this. So if it is even, then it is minus even. That then only we can form cuboid. Now we have what we have drawn, that from this body we have just taken out a small cuboid here. This is again representing the same point. And now we have drawn the three independent planes. If there are three independent planes, then there will be three traction force also.
Yes.
We have drawn these traction vectors, and what we did, we have done that each traction vector can be decomposed along x-axis, y-axis, and z-axis, or x1, x2, x3 axis. That we have done, and we have written these equation using that. Okay, up to this, no problem?
No, sir.
Okay.
Clear.